Hello everybody, we are going to be talking today about how to get a basis for the null space of a matrix A. Alright, first of all, here is our matrix A. It's got 3 rows and 4 columns, so notice, right, it's a 3 by 4 matrix, and that's like our M, and that's our N, and the null space is always a subspace of our N, which in our case, N is 4. So ours is going to be a subspace of R4. So the vectors that we find in our basis should have 4 entries. All right. So here's how we find a basis for the null space. What you do, well, first let's remember what the definition of the null space actually is. Okay, and remember, null space is solutions to AX equals 0. So all you're doing is something that you've done a zillion times before at this point, and row reducing this to solve. Okay, so let's go ahead and row reduce. We already have a 1 up here. So what I am going to do is use that 1 to clear out this 3 below. So we're going to do -3 times R1. That'd be -3, 0, -3 times -3 is 9, -3 times 2 is 6, and 0. And then we're going to add those together to get our new row 3. Okay, so the first 2 rows don't change. That multiplication was just temporary. And now we add 3 and -3 gives us 0. -2 and 0 gives us -2. 9 and 1 gives us 10. -2 and -6 gives us -8. 0 and 0 gives us 0. All right, so there's our first set of our first row operation to solve this system. And now we see we already have a 1 here in the second pivot spot. That's great. So we're going to need to use that 1 to clear out this -2. But if we notice, right, everything in this row, including the zeros, is divisible by 2. So let's take that row. I guess let's not divide by -2. Let's divide by +2. And see what we end up with. So first row stays the same. Second row stays the same. Third row we divide by 2, so we get 0. -2 divided by 2 is -1. 10 divided by 2 is 5. -8 divided by 2 is -4. Okay, and very conveniently, we see that row 3 is exactly the negative of row 2. So we're going to add those together, and we can see that what happens when we add those together is this whole bottom row zeroes out. Right, because all of these entries add to 0. Okay, so then we have to check, are we in reduced echelon form? Both of our pivots are 1s. They are the only non-zero entries in their columns. There's zeros otherwise. The row zeros is at the bottom. So we are in reduced echelon form here. And now we want to use this matrix to write our solutions, right? So we're writing our solutions to find a basis for the null space. You want to write them in parametric vector form. 4 columns in A means 4 columns in our vector here. And remember, anytime we have a variable without a pivot, that's a free variable. So we have 2 free variables here. And let's go from there. Okay, so x1, So we'd have negative 3x3 and 2x2, but we move those over to the other side. So that's 3x3 minus 2x4. I said x2 earlier, but I meant x4. And then x2 is going to be 5x3 minus 4x4. x3 and x4 are free. Okay, so we stay here, and now we want to convert this to parametric vector form and separate into an x3 column and an x4 column, and then also move the variables out front as scalars. So we're going to have an x3 one plus an x4 one. Okay, and basically write the x3, right, there's 3 of them here, 5 of them here, 1 of them here, none of them in the last one because it's just x4. And x4 got negative 2 here. In the second entry, it's a negative 4. There's no x4s in the third entry, and there's 1 in that last entry. Okay, so now remember what we're finding here is things in the null space. So all x in the null space looks like this. Okay, which is great for us. Basically, right, we parametric vector form automatically gives us a way to write entries of the null space as a linear combination of these two vectors. And if we look at these two vectors, right, this one has a 0 right here, and there's a 1. This one has a 0 right here, and there's a 1, and we see like we're not going to be able to get this one as a linear combination of this one or vice versa. Okay, so let's call this, say, V1 and this, say, V2. V1 and V2 are linearly independent, which is great for us because anything in the null space can be written as a linear combination of these. That gives us the spanning requirement of a basis. And then they're linearly independent, so that gives us the linear independence requirement of a basis. So we get that our answer here, our basis for null A, basis is a set, so I'm going to write it in set notation, is these two vectors. All right, great. So there is our answer for this particular problem. Okay, a couple of things here. Okay, so notice, let's go back up to our reduced echelon form. Our reduced echelon form here, we had 2 pivots and 2 free variables, right? And because we had 2 free variables, we got 2 pieces in our parametric vector form. So we're always going to get this correspondence of the number of free variables is equal to the number of vectors in a basis for the null space. All right. So that is one thing that we notice here. Another thing that we had was these 2 vectors that we got out from parametric vector form were linearly independent, and that is always going to happen. So these vectors you get from solving AX equals 0 in parametric vector form are always linearly independent, which basically means this is always how you get a basis. So to get a basis for null A, okay, you solve the homogeneous equation, AX equals 0. You write that solution in parametric vector form, and then the vectors that you get there, okay, the vectors there are your basis. And that's it.